Hi, thanks for attending this talk. The title of this talk is Memory Approximate Message Passing. I'm Lei Liu, and Shunqi Huang and Brian Kokoski are the co-authors of this work. We are with School of Information Science in Japan Advanced Institute of Science and Technology. Full version of this work is available on arXiv. You can download from this link. And this is the content of this talk. First, I will introduce the problem formulation and the existing AMP, orthogonal AMP, vector AMP algorithms. And then I will propose a new memory approximate message passing, including algorithm, main properties, optimization. And I will also show you some simulation results. And I'll finish this talk with conclusions. First is a proper formulation. We consider a very simple linear system consisted by two parts. First is the linear constant gamma, y equals to ax plus m, where n is a Gaussian noise, and the x is a message vector, and A is the measurement matrix. And the second condition is nonlinear constant, that all the element of X follows the same distribution, Px. We assume that A is a right unitary invariant matrix and with a very large size, and Mn goes to infinity. And the goal is to find a posteriori estimation of X given these two conditions, the linear constant of gamma and the nonlinear constant phi. For Gaussian distribution, Px is well known that the global optimal solution is a linear MMSE. However, for some discrete or non-Gaussian constant phi, then the optimal solution is generally NP hard. Then is the existing AMP, OMP, and VMP. AMP type algorithms are used to solve this problem, and we can see we use a local linear estimate gamma t for the linear constant gamma, and we use a local nonlinear estimate phi t for the nonlinear constant phi. The AMP algorithm is given by these formulas, and we don't go to the details of these formulas. And the key point of AMP is that it is Bayes optimal, and it has a very low complexity since it only involves matrix vector multiplication. But the weakness of AMP is it only works for IID measurement matrix. And for some related or the real conditioned matrix, AMP does not work well. OMP and the VMP are proposed to solve the weakness of AMP, and it is given by these formulas, and I will also don't go to the details. The key point of OMP and VMP is also Bayes optimal for any unitary invariant matrix, but the weakness of OMP and VMP is that it involves high complexity linear MMSE operation. For example, here it involves a matrix inverse for large matrix. So this is the motivation of this work. As we show, the existing AMP type algorithms has some weakness. For example, AMP is limited to IID measurement matrix, and the OMP and the VMP has high complexity MMSE. So our question is, can we design an algorithm for all these properties that is Bayes optimal, works for general unitary invariant matrix, and also has low complexity? And the answer is yes, we propose a memory AMP with all these properties. Then I will show you the memory AMP. First, I would like to compare the non-memory and the memory iterative process to you. And for the non-memory iterative process, as shown in this figure, all the local processes are only involves the current input xt and rt. And to solve the correlation problems in the iterative process, we need the orthogonalization between the current input and the current output of each local process. Then for memory iterative process is shown in this figure. The local processor gamma t involves multiple inputs, not only the current input xt, but also all the previous input x1 to xt minus 1. And to avoid the correlation problems in the memory iterative process, we need a stricter orthogonalization. That is, we need a orthogonalization between the output and all the multiple inputs of x1 to xt. This is the memory AMP algorithm. And I will don't go to the details of these formulas, and I will show you some intuitions of this algorithm. First is that we consider memory match filter for the linear estimate. For example, you can see here we only involves matrix vector multiplication. Therefore, the complexity of memory AMP is quite low. is comparable to AMP. Second is that the memory linear estimate is a Taylor series approximation of the linear MMC in OMP and WMP. Therefore, we can ensure a Bayes optimal property for the memory AMP. Third is that we use a memory term for the memory LE to satisfy the orthogonality, and therefore we can get a correct state evolution. Last, we consider a damping for the nonlinear estimate and to ensure the convergency. The memory AMP is based on this assumption that we assume that the minimum and the maximal eigenvalue of AAH matrix is known. And also we know the trace of matrix AAH to the power T. This is just a weaker assumption. For certain random matrix, for example, ID Gaussian matrix, this can be analytically derived. Otherwise, we can use a lower bound for the minimum eigenvalue of this matrix and use a upper bound of this maximal eigenvalue of this matrix instead. For lambda t, we can use a low-cost iterative process to give an approximation of lambda t by this process. It only involves matrix vector multiplication, so the complexity is also quite low. Then we go to the properties of memory AMP. First is that the memory linear estimate of memory AMP is a Taylor series approximation of linear MMC in OMP and WMP. And we designed the efficient T and PT to satisfy these conditions. That is, the memory LE can be right X plus equivalent noise, and the trace of this matrix is 0. Therefore, we can ensure the orthogonalization between the error of RT to X and is orthogonal to all the errors of the impulse X1 to XT. And based on the orthogonalization, we can get a correct state evolution for memory AMP. And the mean square error of memory AMP can be checked by these formulas. And different from the AMP and the OMP and WMP, it just uses a scalar variance for the state evolution. Since memory involves, then we need a covariance matrix for the state evolution for memory AMP. This is the most important property of the memory AMP. We assume that the system is very large, and we consider a right unitary invariant matrix. And the optimized memory AMP converges to the same fixed point as OMP and WMP. Since OMP and WMP is Bayes optimal if it has unique fixed point, so the proposed memory AMP is also Bayes optimal if it has unique fixed point. Now I will show some key intuitions for the proof of this theorem. First is the memory linear estimate is a Taylor series approximation of the linear MMC in OMP and WMP. Second is we use orthogonalization to guarantee the state evolution of memory AMP. Last, we use damping to guarantee the convergency of memory AMP. This table gives the complexity comparison of the existing AMP type algorithms. And we can see AMP, CMP is a recently algorithm, convolutional AMP proposed by Kegel in this reference. And as we can see, the complexity of these three algorithms are almost the same. And we consider the size of A are M by M, and the number of iterations is T. And in general, the iterations is much less than the M or M. And then the complexity of the AMP, CMP, and the memory AMP are MMT. And however, for OMP and WMP, the complexity is M squared M. So it's much higher than these three algorithms. This table gives an overview of the AMP type algorithms. AMP is limited to ID matrix, and the Bayes optimal OMP and WMP needs high complexity MMC, and the low complexity MF, OMP, and the WMP, the performance is suboptimal, even the complexity is low. And the convolutional MP proposed by Kegel, it diverges in high conditional numbers. However, the proposed memory AMP avoids all the weakness of the existing AMP algorithms. For example, it works for unitary invariant matrix, and it has a low complexity MOF for the linear estimation, and it is base optimal, and it always converges for any conditional numbers. Then is optimization. The parameter theta t is optimized to minimize the spectrum radius of this matrix. And therefore, we can ensure a base optimal fixed point. Psi t is optimized to minimize the mean square error of memory AMP, and it can be solved by this equation. This figure shows the illustration of the optimal solution of psi t. This is a very interesting results. Different from the existing AMP type algorithms that are considered heuristical or empirical damping parameters. And this work we propose an analytical optimal damping vector. It is given by this formula. And then this is used to guarantee the convergence of the memory AMP. Then I will show you some simulation results. In the simulation, we consider a compressed sensing problem, and y equals to ax plus n, and the length of x is larger than the length of y, and the A is a unitary invariant matrix with condition number kappa, and the x is a sparse vector. The element follows a IID Rayleigh Gaussian distribution, and with non-zero probability mu, and the Gaussian distribution for non-zero element in x. And in the simulation, we just set the non-zero probability as 0.1. This figure shows like why we need optimization for memory AMP. This is the mean square error, and this is the number of iterations. This is the optimized memory AMP, and the others are the non-optimized memory AMP. As we can see, if there is no damping, then the convergence of memory AMP is not guaranteed. And if the parameters psi and the theta t are not optimized, then the convergence speed is not as fast as the optimized memory AMP. And this figure gives the mean square error comparison between the memory AMP and the existing AMP, CAMP, and OMP. As you can see, the high complexity OMP and OMP has the best convergence speed. For the low complexity memory AMP, convolutional AMP, and AMP, the memory AMP converges faster than these two. AMP does not work well for correlated matrix or the yield conditional matrix. The point here denotes the state evolution, and the line denotes the simulation. And we can see the state evolution of memory AMP are correct. However, in convolutional AMP, the state evolution is not matched with the simulation. This figure shows the performance of memory AMP for large condition numbers. For example, we can see the conditional number for 100, 1,000, and 10,000. And we can see memory AMP is convergent for any condition numbers. And the damping length L equals to 3 is generally enough, has significantly improvement compared with the damping length 2. For larger condition number, we need more iterations to converge to the target OMP and the VMP. It should be emphasized that the convolutional entropy is divergent for large condition numbers in this case. This figure shows the memory AMP for different compressed rate is given by M over N. For example, we can see that the compressed rate with 0.2, 0.25, 0.4, 0.7, and 1. We can see memory AMP is convergent for any compressed rate, and more iterations is need for smaller compressed rate, less iterations for larger compressed rate. Then we go to the conclusion. The problem of the existing AMP type algorithms are AMP does not apply to unitary invariant matrix, even though it is low complexity. And the OMP and VMP works for unitary invariant matrix. However, it needs high complexity matrix involves. And to overcome these difficulties, we propose memory AMP that is base optimal, applies to unitary invariant matrix, and also has low complexity, and the complexity is comparable to AMP. Based on the orthogonalization, we derived the state evolution for memory AMP, and the relaxation parameters and damping vectors are also optimized to improve the convergence of memory AMP. Okay, that's all. Thanks for your participation. If you have any question, and you're welcome to send me an email to this email address. Thank you.